Hey folks, today we're going to talk about electric fields created by point charges. I'll start with a very simple diagram. If I asked you, if I said, hey, there's a positive charge right there, and I said draw the electric field created by it, you would hopefully draw outward lines. And again, what are those lines based on? They're based on what would happen if I put another positive charge near this one. So we're going to call the charge making the electric field, we're going to call him big Q. And let's say I put a little q there, and let's say they're both positive, okay? So what would the big Q do to the little q? Well, they would repel, push away. So that's why that line right there points to the right. If I put a little positive test charge there, that charge will be pushed to the right. Now, you'll notice the electric field varies with distance from the charge. As you get farther away from the charge, the field lines get farther apart, which means the electric field's getting weaker as you go. What's the equation for that electric field? Well, from the previous discussion, electric field is defined as the force per charge on something. Okay. Um, Now, this charge is this guy that we're putting in the field. Okay. Well, what's the force between those two charges? Well, we already talked about that before too. That's Coulomb's law. That's K times the big charge times the little charge over R squared. Now remember, K is about equal to 9 times 10 to the ninth. I'm not going to continually rewrite that. It's pretty easy to remember. 99. So all I'm going to do now is I'm going to take this and shove it up there. So we get electric field equals, um, if you take this equation and put it up there, what ends up happening is the little q's cancel. And you get the following, K big Q over R squared. And it should be in the R hat direction. So that is the electric field created by a point charge. Okay, and it's an inverse square law. So if you get twice as far away from the charge, it's going to be a quarter of the field. If you get 3 times as far away from the charge, it's going to be a ninth of the field, etc. Okay. Now, we're going to actually use this in a couple examples, or in one. I'm going to actually just do one example and kind of work out the entire example using that. So let's say you had a situation where you had more than 1 point charge. In this case, let's say you had 2 point charges. Okay. So let's say that you had a positive charge up there and a negative charge down there. And you were interested in this location to the right of the negative charge. And I'm going to give you some numbers. Let's say this top charge was 20 microcoulombs. Let's say the bottom charge was negative 30 microcoulombs. Let's say this distance here is 30 centimeters. And let's say this distance here is 40 centimeters. Okay. What is the electric field created by both these charges? And just for the sake of argument, I'll label them A and B. What's the electric field, the net electric field created by charge A and B at location X? Okay. Well, here's what a pictorial way to look at this. What we're doing is, if I asked you in the previous discussion to draw the electric field created by A and B, we talked about the rules for electric field lines. So for instance, field lines start on positive charges and go to negative charges. So the field would look something like this. Okay, and then it would be it'd be symmetrical in this case. Okay, and it would kind of, up there you'd have a little bit of that, and down here you'd have a little bit of that. Okay, so here's the deal. What we're trying to actually do is find the strength and direction of that red line at location X right there. Okay. Now, you already have some idea of the electric field. It's going to point left and down. It's going to have negative I and j hat components. So what you have to do is you have to figure out the individual contributions of the electric field by each charge, A and B, at that location. Okay, so I'll start with the harder one. That's the A. What field does charge A make at location X? First of all, you need to know how far away charge A is at location X. Now, hopefully, if you look at this, you're seeing that there's a right triangle here, and it's a 3, 4, 5 triangle. I've picked some nice convenient numbers for us. So the legs are 30 and 40, so the hypotenuse will be 50. Okay, now if you didn't have round numbers, you would just do a Pythagorean's theorem and figure it out. Okay, now the magnitude of the charge is 20 microcoulombs. So here's how you do this. You say K, which is 9 times 10 to the 9th, times 20 microcoulombs. So that's 20 times 10 to the negative 6th, and that's over 0.5. That's our distance in meters squared. And if you do that, you get 720,000 newtons per coulomb. Okay. Now, we're going to have to eventually add vectors together because that field points down and right. Okay, that's away from the positive charge. Positive charge makes fields away from it. So I'm going to go ahead and rewrite this in unit vector notation. This angle right here, if you calculate it, inverse tangent of 3 over 4, you get 36.9 degrees. So if I were to write this EA in unit vector notation, you would do, for the I hat component, it would be 720,000 cosine of 36.9. That would be positive. If you do that, you get positive 575,800. That'd be I hat. The J hat component's down, so I'm going to put minus there. And it would be 720,000 sine of 36.9, which when I do that in my calculator, I get 432,300. And that's J hat, and these are newtons per coulomb. Okay. For B, you do a similar process. And this one's a little easier, though, because we got K. The charge B is 30 times 10 to the negative 6th. That's a micro. And by the way, notice I didn't put the negative for the charge itself. I don't worry about that. I just look at direction when I'm all done. Over the distance, which is 0.4, and I have to square that. And when I do that, I get 1 million. I get a big number, 687,500 newtons per coulomb. And that's going to be left. That's a negative charge, so it's making a field toward it to the left. And so what I'm going to do next is vectorially add those two yellow vectors together. Now for B, this is a negative and it's I hat direction. It's to the left. Okay. So what I'm going to be doing is I'm going to be adding this and that. When I do that, the net electric field at location X is equal to, in the I hat direction, if I add those together, I get negative 967,000, sorry about that, 500 newtons per coulomb. And then that's the I hat. In the J hat, there's only one J hat. Here it is, and it's negative, so minus 432,300 J hat newtons per coulomb. And of course, by the way, I make a note, both the X and the Y components are negative, as we suspected from our red line. That's which way our red line's going. You can also Pythag these and get a result. If you get a result, you get just over a million, 1,059,700 newtons per coulomb at, and I get about 24 degrees south of west. Okay. So that's how you figure out the net electric field created by more than one point charge. You find the electric field by each point charge and just vectorially add them together. Now I'm going to add one more thing to this problem. Let's say now I go ahead and put a charge at location X. I put a little positive Q there. Which way is that? What's going to be the acceleration of that little tiny test charge when I put them there? Okay, well I have to first give you the charge. Let's say the charge is 10 nanocoulombs. Okay, now you might recall a nanocoulomb is 10 to the negative 9th. Okay, so what you could do if you were a glutton for punishment and wanted to do a lot of extra work, okay, you could you could figure out the force of A on that test charge, and it would be a vector, and it had components. And you can figure out the force of B on that test charge. It would be a vector. It would have components. And then you could vectorially add those two forces together. However, I'm not a glutton for punishment. I'm going to do this the easy way. I already have the electric field at point X. It's this stuff right here. Here's the electric field. And I know that the force on any charge is equal to Q that I put times the electric field at that point. This is Q, and this is E. So all I got to do is take Q times E, and that'll be force. So force is equal to Q, which is 10 nanocoulombs, is 10 to the negative ninth, times E, which is that number I just circled there. And if you do that, you get the following: 0.0106 newtons. And it's going to be at the same angle, 24 degrees south of west. Or if you're really cool, I would write this as 10.6 millinewtons at 24 degrees south of west. Okay, so that's how you can figure out the net force acting on a charge there. Now, finally, what if instead of putting a positive 10 nanocoulomb charge there, what if I put a negative 10 nanocoulomb charge there? Well, I would not put a negative in the equation here. The answer would still be 10.6 millinewtons, but what angle would it go at? Well, a positive test charge is going to feel a force in the direction of the electric field. A negative charge is going to feel a force in the opposite direction of the electric field. So the only thing I would change there is instead of saying south of west, I would say north of east. So you literally just reverse each of the two cardinal points. Instead of saying south of west, it would be north of east. It would be that way. And that would be the force acting on that negative test charge. All right, I hope that video was helpful, and thank you very much.